are different number bases. These are all expressed in base 7, hence the subscript here, and we're asked to find the sum of these numbers and express that in base 7 as well. Let me try and briefly explain how different number bases work. Obviously I have to if I'm going to work this problem out. It's really quite simple. We need to look at our own numbering system at first. So we commonly use what's called the base 10 numbering system, or the decimal system. And all that really means is we use digits 0 through 9, that's a total of 10 digits, and then in our place value system we have, of course, the units place, the tens place, the hundreds place, thousands place, and so on. But what those really represent are powers of 10. Units are 10 to the 0 power. The tens place, we're really representing how many units of 10 do we have, 10 to the first power. Here we're saying how many units of 100 do we have, that's 10 squared. How many units of 1,000, 10 to the third, and it will keep going like that, 10 to the fourth, 10 to the fifth. If we put a decimal point there, then we have 10 to the -1, 10 to the -2, 10 to the -3, the tenths, the hundredths, those places. So to kind of compare those side by side, in base 7, which this problem is in, it's a very uncommon base to work in. Normally in computer science we use base 2, which is called a binary system, which only uses digits 0 and 1, or we'll use hexadecimal, which is base 16, octal, base 8. I didn't know the name of this, I actually did look it up, so here's another word for your vocabulary. The base 7 numbering system is what is called septenary. It's the septenary numbering system. Anyway, the whole point is, when you work with place value, we're no longer looking at powers of 10, we're now looking at powers of 7. Oh, and by the way, that implies that the only digits we use are 0 through 6. So this still represents units, again that's 7 to the 0 power. But this now represents quantities of 7. So we think of that as how many 7 to the first power, how many quantities of that do we have. We think of how many units of 49 do we have, that's 7 squared. How many units of 343, that's 7 to the third power. And then, of course, it goes on like that. These are 3-digit numbers, so we only need to look up to the 49th place. There are any kind of number base problem, there's two really good approaches. I'll be honest, one takes a whole lot of math, the other takes not too much, but it takes a lot of thinking. We could convert everything to base 10. Of course, we then would have to add those numbers together and then convert back to base 7. That's the method that requires a lot of steps, a lot of math. The other option we have is add in base 7. So we'll have to kind of think in terms of base 7 momentarily, and we can actually carry digits and do all the kind of regular arithmetic, just utilizing base 7 instead of base 10. This will be a quicker method, much quicker. Alright, now that I've gone over all that, I'm going to erase this to make some more room. I think I'll show the quicker way first, and then depending on whether I feel like it or not, I may show the long way. The quicker way really just, we add using place value the same way we would in base 10. These are all in base 7. So we can add vertically, and we can do some carrying. But we have to just keep a few things in mind. For one, there's no digit that we can use above 6. 6 is kind of like a 9 in this case. So the number 7 in base 7 is actually 1, 0. The reason being, this again is the units place, and this is the sevens place. So we have 1 unit of 7 and 0 units. So another example, number 8 in base 10. I really should be writing base 10 here. That's one of those things that's also invisible. If you don't see a subscript, we assume that we're in base 10. In base 7, the number 8 would be 1, 1. Because it's 1 unit of 7, and then 1 unit. It's really 7 times 1 plus 1. So you could make a list just by counting. You could make a short list of conversions. These are all in base 7. So in the problem, we need to add vertically 1 plus 3 plus 6. 6, 7, 8, 9, 10. That's going to represent 10 in base 10, which in base 7 is 1, 3. So just like we would in base 10 arithmetic, we can carry the 1. It's the 3 digit right down here. We now have to add 1 plus 6 plus 1 plus 3. That is 11 in base 10, so it's really 14 in base 7. Write the 4 here, carry the 1, and now we just have one last addition step. 6 plus 3 plus 1 plus 1, again, is 11. So that is 1, 4, written in base 7, so this is the answer C, 1443. Now, dare I show the long way, which I mentioned earlier was just to convert everything to base 10, and then converting back to base 7. I'll try to do this in the quickest way possible. It's really a good idea to watch how the conversions work to get more familiar with converting between number bases. So, 361 in base 7, we wish to convert to base 10. We have the ones place, the tens place, the 100ths place. Here, in all these numbers, we're going to have the units place, the 7th place, and the 49th place. Converting this to base 10 is then just solving the problem 3 units of 49, or 3 times 49, plus 6 units of 7, or 6 times 7, plus a single unit. That does evaluate to 190. And it is 190 in standard base 10. 1 unit of 100, 9 units of 10, and 0 single units. 613 in base 7. We have 6 units of 49. 1 unit of 7 plus 3. So all of that evaluates to 304. This is 304 in base 10. This is also in base 10. And the last number is 136. 1 unit of 49 plus 3 units of 7 plus 6 units. And that does evaluate to 76 in base 10. So then we add in base 10 190 plus 304 plus 76, 570. The trick with that, and the answer is all in base 7, we have to convert this back to base 7. And that's kind of tricky because it involves division and subtraction. It's a little bit time consuming. Anyway, let's set this up. It's going to be a 4-digit number. So we're now in base 7. So we have the units place, the 7th place. 7 squared is 49th place, and 7 to the 3rd power, 343. So that is a place value as well. 570 does have 1 unit of 343 in it, so what we do is we take 570, subtract 343, and we get 227 left over. So if we account for 1 unit of 343, we have 227 left over. We want to see how many 49s are in that. So if we divide 227 by 49, we get 4 point something. So there are 4 units of 49. Now if we do 4 times 49, we get 196, so we need to subtract 196 here, since we're accounting for 4 units of 49. So 227 minus 196 leaves you with 31. You want to see how many 7s are in 31, so we can divide 31 by 7. We get 4 point something, so there are 4 units of 7 in 31. 4 times 7 is 28, so we need to take 31, subtract 28, see how much is left over. 31 minus 28 is 3, so there are 3 units left over, so we do get 1443 in base 7. Same answer, in my opinion, much more arithmetic. Alright, number 24 is a base conversion problem, and we're dealing with a few different bases. Base 16, which is commonly called hexadecimal. Base 8, commonly called octal. Base 4, which I don't really know the common name, and then we want to convert all this back to binary, which is base 2. There are tricks to doing this so that we don't have to do as much converting back and forth as would be necessary. This is a good problem, too, if you are a computer science competitor, since problems involving numbers with different bases are very common on the computer science contest as well as the math contest. So there's a trick with converting all of these different things to base 2 specifically. Base 16 numbers, each digit itself will represent 4 digits in binary, or we used to call those binary digits or bits. Each one of these will be a group of 4 different either 1s or 0s. In base 8, each of these goes to 3 bits. We can write them side by side using 3 bits. And of course in base 4, each of these is only 2 bits. So what we want to do is we want to convert all of these to binary using these rules, and then add them in any order really, and get our solution in binary. So A1, as I've said before, can be converted to really to a total of 8 bits. The number 1 expressed using 4 bits would be 0, 0, 0, 1 in binary. A, this digit, again represents the number 10 if we're looking at hexadecimal. In other words, it's the digit that comes right after 9 and represents the quantity of 10. So in binary, 10 is a quantity of 8 plus a quantity of 2. So again, if we do our place value, we have a 1's place, the 2's place, the 4's place, the 8's place. We would have 1, 0, 1, 0. So this right here is A1 converted to binary. And we just want to do the same things for the octal number, which turns into 3 bits each, and our base 4 number, which turns to 2 bits each. 4 in binary is simply, if we have 3 bits lined up, it would be 1, 0, 0. Again, because we have the units place, the 2's place, and the 4's place. 3 is 2 plus 1, so we can have a 1, a 2, and no 4's. Kind of reading that right to left, because we want to do place sign here. So 2, again, is no quantities of 1, 1 quantity of 2, and no quantities of 4. So this, again, is 234 base 8 in binary. One last one, 3, 2, 1, 0. We want to make these 2 bits each because we're in base 4. So 0 is just 0, 0. 1 is 0, 1 in binary. 2 is 1, 0. And then 3 would be 1, 1. So our goal is now to add these 3 numbers in binary, and that will give us our answer. Let me write these from right to left to make sure we line our digits up. So this A1 is 1, 0, 0, 0, 0, 1, 0, 1. From right to left here, it's 0, 0, 3 1s, 2 zeros, a 1, and a 0. And then here we've got 0, 0, 1, 0, 0, and 1, 1, 1. So I'm going to add these all together. And just remember that we're in binary, so things like if we had any quantity that was 2 or larger, just remember that 2 is 1, 0 in binary, 3 is 1, 1 in binary. We can use that information to carry digits over. And let's just add column-wise. We have 1 plus 0 plus 0, which is 1. 3 zeros is 0. 0 plus 1 is 2, which is 1, 0. So we can carry here 1, 0. 1 plus 1 again is 1, 0, so carry the 1. Here again, because we carried the 1, we have 1 plus 1, which is 1, 0. And here we have 3, which is 1, 1. So we're going to count 1 down here, also carry a 1. 1 plus 1 is 1, 0. This gives us the quantity of 4. 4 again is 1, 0, 0 in binary. So 1, 0, 0 is the last digits that we write. This is the sum in binary, and that is answer choice A.